Hi everyone, I'm Anne. Today, I'm going to be presenting the brief announcement, Efficient Access History for Race Detection. One of the challenges for writing task parallel programs is determinacy race. It occurs when two logically parallel instructions access the same memory location, and at least one of them is a write. Determinacy race can lead to non-deterministic results. They are often bugs. Let's look at this task parallel code on the right as an example. We refer to a block of codes that only contains a sequence of sequential instructions with no parallel constructs like spawn or sync as a strand. So in this example, we have two parallel strands, strand 1 and strand 2, and they write different values to the same variable x. Then, in the main function, we output the value of x. Since strand 1 and strand 2 run in parallel, the output value can vary, depending on the scheduling order. Such bugs are hard to debug, because determinacy races do not necessarily produce wrong results in every single execution. Therefore, race detection tools can be helpful in this regard. On-the-fly race detector is a kind of race detection tools that runs during the execution of the task parallel program and checks if the program has a race. A race detector has two components: an access history component that records strands that have accessed a given memory location in the past. It turns out that it is sufficient to record a single reader strand and a single writer strand for sequential race detectors. The other component is the reachability analysis, which determines whether two strands are logically in parallel. For example, when reading a memory location, we use the access history to find a previous strand that writes to this memory location. With a previous writer found, we then use the reachability component to check whether it is in parallel with the current reader. Something similar happens when we check for races between two readers or two writers. In the interest of time, I will omit the details here. In this work, we are interested in optimizing access history, which is an expensive component of race detection in practice. Most of the prior work used a hash map for access history. The hash map maps each memory location to its previous accesses. As an abstract example, say we have memory locations 1 to 20. Locations 1 to 8 were previously accessed by a strand with ID A. Locations 9 to 13 were accessed by strand B. Locations 14 to 20 were accessed by a strand C. The hash map will contain 20 entries of memory location and its previous accessor. In general, the size of the hash map is as big as the number of memory locations written and read. In theory, inserts and queries on access history incur constant overhead. However, as we can tell from the figure, such a hash map-based scheme incurs significant overhead in practice. This is because access history must be queried and potentially updated on every memory access. So in this work, we would like to reduce the overhead on access history. We observe that each strand in the task parallel program typically accesses contiguous memory locations. Thus, our idea is to coalesce the range of such contiguous memory locations accessed by the same strand and store them as an interval. Following the previous example, we will only keep 3 intervals in this case. This way, as the number of intervals can be significantly smaller than the number of memory locations, we store fewer entries and invoke fewer inserts and queries. Empirically, we have also shown that the number of intervals is much smaller than the number of memory accesses for both read and write. The bar charts detail the comparison for 7 benchmarks. Now that we have a set of prior intervals, with any new interval coming in, we need to find all prior intervals that overlap with this new interval and check races between them. For instance, we have these 3 prior intervals. Now, a new strand D accessed memory locations 7, 8, 9, and 10. We generate a new interval with the range 7 to 10 and accessor D. We refer to this interval as interval D. To update the set of prior intervals with interval D, we first find all overlapping intervals. In our case, we have intervals A and B. Then, we check races between A and D, and between B and D. If there is a race, we report it, and the program terminates. Otherwise, we update the set of intervals by shrinking intervals A and B and putting in interval D. For illustrative purposes here, this example is based on write intervals only. For read intervals, the update procedure will be similar, but a bit more complex. In order to support such efficient inserts and queries, we use a variant of interval trees to maintain the intervals. As we have seen from the example, we enforce an additional non-overlapping property that no 2 intervals in the tree overlap. Theoretically, it takes big O h plus k overhead per interval to insert or query, where h is the height of the tree and k is the number of overlapping intervals. This bond will be better than paying overhead per memory access if the size of intervals is sufficiently large. To wrap up, we optimize the access history component by coalescing contiguous memory accesses. To that end, we modify the compiler and runtime system to generate intervals for each strand, and use a novel interval-based tree data structure to maintain access history. We evaluated our optimization by applying it to a sequential race detector for task parallel programs. Results show that we have successfully reduced the overhead of access history. Specifically, our race detector incurs 18.61 times overhead on average. In comparison, race detector from prior work incurs 78.13 times overhead. This is a 76% reduction in race detection overhead. Here comes the end of the presentation. Thanks for watching.